All right, reviews of CNN. Really, we've looked somewhat at putting convolutions together into an entire neural network, but we're going to really look at that today. We'll review the convolution part of that, and then put that together with a neural network. So CNN convolutional neural network. So a reminder, we have these kernels, which are shared across all of the pixels in the input image. Right, so if we've got an input image that's, I don't know, looks like that. We're going to be running this kernel or this filter over this image everywhere in it, and come out basically with outputs for every pixel as to whether that kernel gives us a big number or a small number. Often our kernels are 3 by 3, but they can be larger. 5 by 5, 7 by 7 is not uncommon. Larger than that is fairly uncommon. We'll see as we get into some architectures later on how, so it'd be nice if the model could tell you, if the training could tell you whether it really needs a 3 by 3 or a 5 by 5 or a 7 by 7. And so we will look next week at some architectures that say, well, instead of doing 3 by 3 or 5 by 5 or 7 by 7, let's just try all of them and kind of let it learn which ones that it wants best. But for now, we're going to go straight to the 3 by 3 kernel. If we have, let's say, a 22 by 22 input, and we run it through this kernel, what sort of output are we going to get? What's the size of this output?
Doesn't depend where we start the kernel.
It depends on where we start the kernel. It depends on the padding that we use. So it depends on padding. So if we do no padding, that means that this kernel, the top left of this kernel has to align with the top left of this kernel and so on. So what's going to happen to our 22 by 22?
It'll become 20 by 20.
Yeah, it'll become 20 by 20 because we'll have, if we look at the center of this can't be at 1, 1. It'll have to be at 2, 2. And down here, the center can't be at 22, 22. It'll have to be at 21, 21. So we'll basically go from 2 to 21, which is 20 by 20. Sometimes we like that shrinkage, sometimes we don't like that shrinkage. If we want to avoid that shrinkage, then we set the first pixel that we center this at as 1, 1, which means we're going to be looking at pixels outside the edge. So we basically pad it with zeros. Right? In this case, we're going to have an overlap of 1, so we'll need a padding of 1 all around. If we had a 7 by 7, how much padding would we need? Stanton?
We need 6, no, 3.
3, right, because we're centering the 7 by 7 at 1, 1, and that's going to have 3 up off the top and 3 up off the bottom. So we can have no padding. We can be half padding, or no one really uses full padding, which basically says, let's put this at 1, 1 to begin with. All right. Let's go ahead and use half padding, so this can be 22 by 22. Okay? And let's extend this to 3 dimensions. So this is still 22 by 22, but it's a nice color, 22 by 22. Right, so we've got red, green, and blue here. So 22 by 22 by 3. This kernel now has to get bigger too, right? We don't want to be operating on each of these planes independently. We don't want to say, okay, let's look at the red channel, or the red plane, and do convolution on that, and then separately green and separately blue, because there's definitely information in here. We may have trying to think of what we might have, I don't know, a little kernel that's trying to find a red thing happening here and a green thing happening here. And so it needs to be able to look at the red and the green simultaneously. So we're going to extend this kernel to be 3 by 3 by 3. Okay. This 3 by 3, we get to choose. Right? We chose how big the convolution is. This 3 is this 3.
You're saying how we want to keep the colors together, sort of? Is there a way to keep them apart? Can we separate them? Is that necessary?
Yeah, we could come up with sort of a one-dimensional convolution here and apply it to each of these separately. So that would be possible to do.
That makes sense.
And our 3 by 3 by 3 convolution here, right, so this 3 is equal to this 3. They need to match so that as we move through, we're operating on the right number of pixels. How deep is the output here? Ezra?
How deep is it?
Yeah, is this 22 by 22 by what?
Should it be 3?
So let's think about that, 3. We got 27 weights in here, right?
Yeah.
If we look at a particular, let's say we start at the top left, we're going to be looking at 9 in this plane, 9 in this plane, and 9 in the back plane, right? And we're going to be multiplying basically these 27 values by these 27 values and summing them up. What do we get as a sum?
Something pretty big, I bet.
But it's how many numbers?
How many numbers?
Uh-huh.
3 numbers multiplied.
We got 27 here, right? So we got 9 and 9 and 9. And these are all being multiplied by the associated 9 and 9 and 9.
Oh, so it's 6 total.
9, 27 all multiplied together and then summed up. Right, so we're going to have this value times this value,
Yes.
plus this value times this, plus this value times this, and we keep going for these 9. And we keep going now for the green ones. Do the same thing for the ones behind this. And then the blue ones for the ones behind this. We add them all up.
It's going to be like cube.
So it's going to be, in the one-dimensional case, it was 9 numbers, 9 pairs multiplied and added. And here it's 27 pairs multiplied and added. So it's basically a summation over I, J, K of our original input, I, J, K, times the kernel. Let's not use K for that. Let's use F for filter, I, J, K. So 3 values for I, 3 values for J, 3 values for J, 3 values for K. We get these all, and this just gives us one number, right? So for 1, 1, we have one number here. We're going to put one number in here. And one number in here, and so on, all the way for these 22 by 22 different values. So the depth is just 1. So one kernel, also called a filter, gives you this, which is the feature map for this particular feature. So it tells you spatially what's going on with regards to this kernel. And of course, we're sharing weights here, so we're using the same weights in the top left as we're using the bottom right, as we're using the top right, as we're using the bottom left. Does this make sense? Reminders. But one kernel's not enough. Because we might have a lot of different things we're looking for. Horizontal lines, little whiskers, splotches of red. And so we're going to create multiple such kernels. So we're going to have K kernels. Each one gives us a 22 by 22 by 1 output. And if we smash them together, then we're going to have 22 by 22 by K. So the first plane will be the output of the first kernel, second plane output of the second kernel, third plane output of the third kernel, and so on. They're arranged spatially correctly, right? 1, 1 here is the information about 1, 1 from the first kernel, from the second kernel, from the third kernel, from the fourth kernel, and so on. So it's still spatially correct. Does that make sense? And then once we have this three-dimensional feature map, we can now feed that into another layer of convolutions. So let me show you some things that I have left out. One thing I have left out is a bias. We used biases before when we were doing, XW plus B. Now we need a bias as well. So we really need to add a bias here. So it's a summation plus we have some bias B. So every kernel has a bias that goes along with it. So we don't really have 27 weights. How many do we have? 28 for every one of these kernels. A lot of times I'm not going to show the bias, but be aware that it's there. So the convolutions take us from a height by width by depth tensor to a height by width by depth tensor. What's the relationship between this height and this height? Josh? What's it depend on?
Is how much padding you need.
So it depends on the padding. What else does it depend on?
The size of the kernel.
The padding, the size of the kernel, and
The actual picture.
the original.
Yeah.
So we take the original height, we take the size of the kernel, we take the padding, and that's going to tell us what this height is. And all the time, heights and widths are the same. Is that all the time? Most of the time, heights and widths are the same. Okay. So the new height is some function that's not very complicated of the old height and the kernel height and padding. And the next thing that I'm going to give you, which we hadn't talked about, which is the stride. So what I assumed before was that as we took this kernel, we went in the original image, we moved one at a time over. That's the stride, how much we move from one pixel to the next pixel. So we had a stride of 1. You could have a stride of 2, so, or more. So let's say we have a 5 by 5 by 5. Let me get my numbers right. Let's see how this will work. 72. We have a I'm gonna do a 6 by 6 with a 3 by 3 kernel. And I'm gonna say no padding. And so if we had our normal one stride, this would turn us into a Willow. We go from 6 by 6 with a 3 by 3 kernel with no padding, that would take us to what size? 3 by 3. So let's see, we have the first one would be centered in 2, 2, right?
Wouldn't they just be the same size?
If we have no, so if we had half padding, if we had padding of 1 or half padding, it'd be the same size. Since we don't have padding, this is where the first kernel is going to go. Right? So this is at 2, 2, and then it'll be at 2, 3, 2, 4, and 2, 5. So 4 by 4. Now let's change the stride from 1 to 2. So if we do stride 2, the first one is going to be at 2, 2, and the second one's going to be at not 3, 2, sorry, not 2, 3, but 2, 4. So first one is here, and the second one is going to be at 2, 4. So this, so. This is the first, and this is the second. 1, 2, 3, 4, 5, 6, and then we're done, right? Because we don't have any padding. So that'll go to a 2 by 2.
Isn't that a 2, 5? Isn't the center at 2, 5? Because it's, shouldn't it overlap through one column?
Let me look at this second. Yeah, the fact that this is 2, 2, 2, 3, 2, 4, 2, 5, this is clearly a stride of 3. Okay? Stride of 2, we have a 1 pixel overlap between them, right? So the first one would be here, the second one would be here, and these numbers wouldn't work out very well because we can't have the third one here because of our padding. Okay, so if you have large strides, it shrinks your output size.
Are strides usually in both directions, or do you usually only do it?
They normally be the same, horizontal and vertical. Yeah, the APIs normally don't allow you to specify a size. We can imagine doing that, but we don't want to. It's not a part of it.
What do you do if there is the 1 pixel?
And you're not doing padding, you would normally just lose it. So in this case, it just wouldn't. It wouldn't go down to deeper layers.
Wait, so about the vertical and horizontal strides yet? So then if you, now in the next step, and you moved down,
If we move down, we would move down whatever our stride is. So we'd be moving horizontally with the stride and vertically
okay,
with
and
the stride.
since there's no like pattern here, we can't move down anymore.
Oh, no, we can move down. Right, we can move, we do stride 3, we can move down from 2, 2 to 5, 2. And then to 5, 5. So our kernel would basically be tiling our input with no overlap.
Is the kernel always going to be a square?
Yes.
Since, yeah,
Yes.
it's going to be the same vertical.
Kernels will definitely always be squares.
Sweet.
I mean, one could define them differently, but they always are.
Can we do stride 2?
We can do, sure. So let's do stride 2, but let's, instead of doing a 6 by 6, let's do a 7 by 7.
Can we do it with 6 by 6?
Okay, we'll do a 6 by 6. So the first one will be at 2, 2. The second one's going to be centered where?
So 2, 4.
2, 4. Right. So the second one's here. And then if we could, the third one would be where?
2, 6,
2, 6, but that goes off the edge, so we wouldn't allow that.
but so it's still.
So it'd still be a 2, 2, where we just lost anything having to do with this bottom and right column. So the last thing here, in as far as our function, is that we also take into account the stride. And it's a fairly simple arithmetic formula. No, I don't think it's worth memorizing. There's another operation. We could do convolutions, where we just do a convolution, we get outputs, then we feed this into new convolutions, do outputs, feed this into new convolutions, do outputs, and so on. The problem is, we don't have any nonlinearity. And so that successive running through convolutions, we might as well just run through one big convolution, basically. So how do we get nonlinearity? How have we done that so far?
Activation functions?
Activation functions. And the simplest activation function that we've used?
Really?
Really. So that's what we would normally do. We will normally have a convolution followed by a ReLU or possibly some other activation function, followed by often another convolution and another ReLU. What tends to happen is that the number of kernels increases over time. So if we start with 22 by 22 by 3, and we start going now to more kernels, let's say we have 5 kernels here, and then we have 10 kernels the next time. If we keep our same height and width, we're increasing the amount of data coming out of each layer. And that can get prohibitive. So often we balance the data at each layer so it's approximately the same. So as we're increasing the number of kernels, we're decreasing the height and width. Okay. We know one way to decrease height and width now. What's that?
When you have padding, when you don't have padding.
Yeah, so if you don't have padding, we know we get rid of at least one. Right? We get rid of half of the kernel size. So that reduces it a little bit. And what else can reduce it?
Stride.
Stride. Yeah, so we can use the stride and padding to reduce the size. Don't normally do that. Normally what we say is we use an operation that cuts it by a factor of 2. So it's a new operation. It's not a convolution operation. It's a pooling operation. So the pooling operation is basically going to take 4 pixels that are in a square and turn them into 2. So it's going to take, let's say you have, let's just look at the operation itself. Max pool takes four to 1. So given the name, what do you think max pool takes these 4 numbers to? 10.
Pass, for sure.
Okay.
To one number.
To 1 number. What is the number?
Maybe the summation of all.
Okay, if it were called some pool, that'd be a good name.
Or the max number.
Okay, so it is
21.
21. Yes. If it were the other kind of pooling, average pool, what would you want the value to be?
The average of 4.
Okay, fine. Which we will calculate to get 31, 25, somewhere around 6. Okay. So you can see how if we do this on something larger, right? If we do this on a 1024 by 1024, that's going to take us down to, it's basically going to do a 2 by 2 here, and then a 2 by 2 here, and so on. So it's going to tile this from a 1024 by 1024 down to a Roy.
We're using,
It's a 2 by 2 max pool.
okay, so it's gonna be 5, 12.
Exactly. Okay. Effectively, when you do max pooling, if you want to think about it this way, its stride is also 2, and its padding. I guess its padding would be relevant if you had an odd size height or width. We normally just don't, we arrange things so that it's even.
Can we think of it as another convolution? Since the max pool we're using is like a kernel. Yes.
Well, there's two things about it. One, where I'd say no on whether we could treat the max pool as a convolution. So one, we don't have any weight. There's no parameterization of the max pool. The max pool just does its thing of finding the max. If you want to think of it in terms of there's a stride and a padding, kind of as you're moving through and operating on areas of the input, then yeah, you could kind of think of it that way. But it's not learning anything.
So with odd number dimensions, how does the pooling work? Do we just keep?
There are two possibilities. If we do no padding, it's going to chop off. It'll round down. And if you do padding, it'll round up. But I think normally we just don't have any padding on the max pool.
Is pooling always 2 by 2, or is it kind of a parameter that we can control that?
You could control
affect
it.
it one way or another.
Yeah, you could do something other than 2 by 2. I don't think I've ever seen it, but you could. Okay. Normally padding 0, stride is the same as the size. Here's the intuition for max pooling. We're trying to say, okay, we've got a slightly larger area here. We've got these 4 values here, and we want to know, did a feature occur in here? We want to know more like, was there a feature in this area that happened? Like, was there a horizontal line in here? And so max pooling captures that better than average pooling. Because in average pooling, if there was a horizontal line here, but not here, not here, not here, then we get like, not really a horizontal line. But we want to capture there was a horizontal line somewhere here. And so the max does that. Let's say we do questions on the max pooling, and now I'm going to put it together with convolution.
Actually, a question, is this related at all to like dropping layers of neural net, or is it different?
Dropping layers. Tell me more. Could you mean dropout by that?
Yeah.
Okay, no, it's not related to dropout. We will talk about dropout one day. So here's what we're going to do. We're going to have a convolution followed by a ReLU followed by a max pool. So this is 2 by 2. This is a 3 by 3 with half padding. That is padding 1. Stride 1. We've got how many of these? We've got 10 kernels. Our input is 128 by 128 by 3. What is the shape of the output from convolution? Jack. So we've got this convolution, we're feeding it a 128 by 128 by 3. What are we getting out in terms of our size?
Should we have a, so we're applying, have that and we're applying the current convolution to it. So we should get, we should have, what should be 10 on the, for the depth.
Okay, I'll agree with 10 because we've got 10 kernels.
And then I guess, is it just gonna be 64 by 64?
No, it's good. So I'm not doing the ReLU with max, right? Just the convolution.
Okay.
So just the convolution, it's a 3 by 3 convolution. We have the normal stride of 1. And we have one padding all around.
One pattern. So it's gonna be 128 by
128 by 128. Exactly. Everyone get that? Make sense?
Can our max pool be considered like an activation function? And then like, so we don't need to do like a ReLU.
There is a nonlinearity to it. So if it were average, that wouldn't, right? But a max, yeah, I guess it could. I never thought of that. All right, now we do a ReLU. Does a ReLU change our dimensions? Now, ReLU basically is taking every number in here, and it's negative, turning to 0. So I'm going to leave that alone. And now we do our max pool. So the question is, what's the size of this? Ali. So we have a 128 by 128 by 10 coming into the max pool. Coming out of the max pool. What are our dimensions?
64 by 64 by 10.
64 by 64 by 10. So that is exactly right. Unlike a convolution, right? The convolution operates on the entire depth of this at once. So the convolution is 3 by 3 by, in this case, 3, right? So it's operating on all of them. The pooling is operating on each plane independently. So it's just doing a 2 by 2 for the first plane, a 2 by 2 for the second plane, a 2 by 2 for the third plane, which kind of makes sense because we're just trying to summarize the information here into a smaller spatial area. And so we're losing some fidelity, right? We know that if there's a large number here, like 121, we know this means that in the first plane, that is the first kernel, or the first filter, there's something going on. If 121 is a high number, there's something going on in here. How does that relate to the original pixels in our original image? And that, well, let's look at that 121 right there. The question is, what is the receptive field? Which means, which of the original pixels affected this 121? Did the top left pixel affect it? Yes, because the top left pixel here affects the top left pixel here, right? And the top left pixel here affects the top left pixel here. They're not really pixels anymore, but let's say that that's the case. So in fact, we know these 4 pixels affect this pixel here. So the receptive field of this is the same as the receptive field of all 4 of these, the union of that. What about the receptive field of this in the top left here? What pixels here affect that top left one? Is it just the top left one? No, because we're applying this 3 by 3 kernel. right? So the 3x3, the first iteration of the 3x3 kernel is like this, right? So it's affecting pixels 1, 1, 1, 2, 2, 1, and 2, 2. So receptive field here is 1, 1, 2, 2, 2. Just providing the top left and the bottom right. What about this one? It still includes 1, 1, right? Because we moved over, shifted over our matrix over 1. And so now it's including this pixel, this pixel, this pixel, this pixel, this pixel, and this pixel. Agreed? So this is 1, 1, 2, 2, 3. And this one? Volunteers.
1, 1 to 3, 2.
1, 1, 2.
Oh, wait, which one are you doing?
This bottom right one here.
Oh, 1, 1 to 3, 3.
1, 1 to 3, 3. I would do that. I'm really just mentally placing my 3, 3 map there. And then finally, this one is over 1 to the left. So if this one is 1, 1, 2, 3, 2. So if that's the receptive field for all 4 of these, then this is just the union of those receptive fields. So this is from 1, 1 to 3, 3. Right. So anything happening down in this part of the picture can't be affecting this. It's important as we move on in the depth of our neural network that a receptive field increases. Because we want to be able to capture some features. You might have a feature, that recognizes a kindergartner's painting. You know how they always have like a sun up here, and then they have like a house down here. Right? You need a receptive, if you want to capture, yeah, that's one of those sun house kindergartner ones, right? You need to capture there's a sun and a house. So you have to have a receptive field somewhere down the line that includes all of this picture. That's another reason why we're shrinking and shrinking and shrinking. So that we've eventually got, something that's really small and where each of these receptive fields includes the whole picture. Or at least much of the picture. Does that make sense? Okay? Because if you move down in your neural network and you didn't have the receptive field that included this together, there was no way to say you had both the sun and a house. And you might even want to have a kernel that sort of says a sun to the top left and a house to the bottom right, which we can do with a 3x3 kernel, right? As long as our inputs coming in had a feature map that included for one of the planes sunness and another one that included houseness, then we could construct ourselves a kernel that had sunness at the top left and houseness at the bottom right. Convolution ReLU, and then we'll have a pool. And really what it often looks like is this, if I use regular expression syntax. Convolution ReLU repeated once or more. I guess theoretically that should be a plus in regular expression syntax. Followed by a pool, and that we repeat. And these convolutions normally will have the number of kernels increasing. So The pool will take care of decreasing our height and width dimensions. The increasing filters will take care of increasing the depth. Do the height and depth of whatever's incoming affect the number of weights we have? Or the height and width. So if the height and width is bigger, does that change the number of weights in our kernel? No. We just take the same kernel and move it around however big it is. So that doesn't affect it. The depth does affect it. Right? The larger the depth is, the larger the kernel depth has to be. Let's look at a video. So this conceptually shows what's happening with convolutional neural net. Let me explain. So we got an A. We're trying to recognize an A. And we get this convolution that's running across all of the input pixels, generating this feature map. Okay? This is for one kernel. We're going across, and it looked like some edge detection. So notice it's kind of finding the diagonal edges maybe. And then we get to the very bottom, and then we get to the very bottom, we get to the very bottom, and then we say, okay, let's do the same thing for a new kernel. Okay, so this is a different kernel that's going to be finding different things. So this one we created here is going to be the first plane in our output. This is going to be our second plane in output. However many kernels we have tells us how many planes we have. And now we put those two together, so we got notice the different planes. And I'm not sure what that thing just was. We got them together, and now we're running convolution, and it's doing both depths at once, right? So it is able to read from both here and here together. And then it does it for another kernel. Right? So this is a 2-layer convolutions. There was a ReLU in here we ignored. And then finally, when we're at the end, we kind of will do a, this is very conceptual, but we'll basically have our output and we will run that through a fully connected layer to some sort of a, in this case, a softmax.
So what was the output in there that they were checking against? Like how did it represent the different letters? Because it looked kind of, but it wasn't clear to me how like one was A, one was B, one was C, one was D, one was E.
So, this is so helpful. Go there and stop. All right. So what this was the output of, we had 2 kernels coming out. So we had our first layer that came in, and this was the second layer outputs. And so this was the 2 planes separated side by side. How would actually do this connection? Just think of that as a simple neural network that just learned some weights here to figure out kind of, here is some input, here is some output. As we get to the end of our convolutional neural network, we'll have some final thing that looks like this, of some height and some width and some depth. It's a bunch of numbers. If we're trying to recognize digits, or those letters, if we're going to recognize 5 letters, then we'll take a fully connected layer from each of these values, each of the 64 by 64 by 10 values, to the 5 possible outputs. Maybe we'll even have 2 fully connected layers to just take all this high-level information and figure out which parts of this are useful and what sort of weights to get to our final classification.
Yeah, I guess my question is more like what is the format of the Y in this? Like what are they checking against? Because it looks like
The Y really would just be A's, B's, C's, D's, and E's.
yeah, but in what form?
probably a one-hot encoding.
Okay.
Okay, so this part is conceptual. Think of this as a last little neural net, regular old neural net, that is connecting us from these fairly high-level features we've gotten.
Okay.
Let's, I guess, look at an example. Do you remember when we did the MNIST example, which is recognizing digits? And we just created a couple fully connected layers. I think it was 2 or maybe 3 fully connected layers, and we trained it, and we got, I remember what it was, like 88% accuracy, and it trained really quickly, and that was nice. We're going to now do the same sort of thing with a convolutional neural networking system. And by the way, at MNIST, that data was used. So I think it was the US Postal Service put out a bid basically for people to do handwriting recognition on, I think it was zip codes. Right? So they wanted to basically so here's how it used to work. Envelopes would come in front of a person and they'd sit there and the person would read the zip code and type in 92373. And then another one come along, 52764, and another one come along. And they wanted to automate that. So separate to this was some code that would identify where the zip code was and extract it. And I think would also extract the digits from it. And now the question is, from those digits, which digit is which? And that's what the MNIST was used for. Right? And it was actually a commercial project. So this is from the Cholette book 5.1. And there's some interesting things to talk about here. So this is our model that we're going to be using to recognize digits. All right, so we've got these very low resolution digits, 28 by 28. We are going to have a 2-dimensional convolution. Why would we have? Sounds like you could have a 3-dimension. What could 3 dimensions be? Well, so we already have, for our 2-dimensional picture, we still already have grayscale there. Right? So we still have a numeric value between 0 and 55.
Would 3D have our kernels not be 3D, so it maintains the 3rd dimension?
The kernels would be
1D?
now 3D by whatever the depth is coming in. So let's think for a second. This is a 2-dimensional image. Well, here's what I'm thinking. Let's say we had a movie, okay? So we have 1040 by 10, what's the number, 1040? 640 by 40, let's say, VGA, right? Red, green, and blue. And then we also have many of those over time. You can imagine a convolution that's operating not only on pixels within a current time value, the red, the green, and blue values, and the ones right around it, but also the ones near it in time. So the ones a couple of frames before and a couple of frames after. So that's how we could use the 3D. In any case, let's look at this. It's 3 by 3. How many do we have? 32. We're going to use a ReLU activation function. The input is going to be a 28 by 28. We're going to have a max pooling layer that's a 2 by 2. And then another 3 by 3 kernels. How many of them? 64. So notice our size has dropped from 28 by 28 to 14 by 14. But now we're increasing the number of kernels from 32 to 64, so our depth is increasing commensurately. We do another max pool, and then we do 64. Let's look at the summary of this. So the nice thing about this summary is it will show us the output shape. So we're going from 26 by 26. Let's look. The input is 28 by 28. The output of the first convolution is 26 by 26. What must the padding be? The padding must be 0. We don't have any padding. So that must mean the default padding for convolution 2D must be 0. No padding. Okay, so we go from 28 by 28 to 26 by 26. We have 320 parameters. Let's just kind of think about that a second. Where does that come from? How many kernels do we have at this layer? We have 32. All right, so it sounds like there's 10 parameters, 10 weights per convolution. Does that make sense? Why 10? 3 times 3 plus the bias. Right, so we've got a 3 times 3 kernel. So 9 numbers, 9 weights, plus the bias. That's 10. Why do we not have any depth here? Why isn't our depth 3? It's 2D, right? Our input, well, our input shape is a 28 by 28 by 1. So therefore, we only need 3 by 3 by 1. So it's because it's a grayscale image. But at this level, we don't know. So we have 320 parameters. Does that make sense? We do a max pooling layer. That takes us from 26 by 26 by 32 to 13 by 13 by 32. No weights, no parameters. There's nothing to parameterize there. So when we run our back propagation, the max pooling is, we're not going to learn anything at that layer. We do another convolution. How many kernels at this layer? 64, because that's how deep it's coming out, 64. And we went from 13 by 13 to 11 by 11, again, because we have no padding. 11 by 11, well, this is a good example where we're going down to 5 by 5. We are losing some information here, right? On the right and the bottom is being lost. And we go from 5 by 5 to 3 by 3, again, because we have no padding. Let's look at this number, 18496. So let's figure that number out. Especially important because your homework is going to be figuring out numbers and parameters. So, how many kernels do we have? So this is the 18496 we're looking at. Let me just make it a little bigger. Number of kernels is 64. Size of each kernel.
It's still 3 by 3 by 1.
Nope. It is 3 by 3 by something else. We know it's 3 by 3 because we don't know it from this summary, but we remember we initialized it as 3 by 3.
It's 32, or 3 by 3 by 32.
It's 3 by 3 by 32 because the output that it's operating on is a 13 by 13 by 32. So this depth of 32 means we have to have 32. Each kernel has to be of depth 32 to match this, because we need to operate on the entire depth of this. So it's going to be 3 by 3 by 32. So it's gonna be 32 by 3 by 3 plus 1 for the bias. So bias kernel dimensions times, how many kernels do we have? 64. So let's just see if this is remotely in the ballpark. This is 2 to the 6th, this is 2 to the 5th, so we have 2 to the 11th times 9, so that's about 2,000 times 9, so let's call it 19,000. 18,496, close enough. Close enough for me. For your homework, you need to go to these ends. All right. So we have 55,000 parameters that are going to be trained here. But this is not enough. We can't take a 3 by 3 by 64. This is sort of, with your question, like what are we going to be training against? What's our y going to be? A 3 by 3 by 64 thing? No, our y is going to be a 1 hot 0 from 9. So we need to take this to actually 0 from 9. So let's actually just run this picture. We have 28 by 28 by 1. We have now 32 convolutions, 3 by 3. That takes us to a 26 by 26 by depth of 32. We take that to a ReLU, which doesn't change the size, and then we take it to a max pool, which takes us to 13 by 13 by 32. And then we take that to another convolution with 64 3 by 3s. So it takes us to, since we don't have any padding, 11 by 11 by 64. And then, what, one more max pooling? We have a ReLU, and then we have a max pool. So 5 by 5 by 64. And then finally one more con, of which we have 64 again. So 3 by 3 by 64. Followed by ReLU. So what we've got is basically 600 odd values here. And what we're going to do is feed them into a fully connected layer. Okay? So flatten basically takes this 3 by 3 by 64 and turns it into a flat 500 and odd, whatever. Okay? So flatten takes this to 3 by 3 by 64. And now we're flat. We know how to do a fully connected layer. So this next layer is how big? 64 big. So we'll do 64 big here, and we'll have a fully connected layer. Right? which afterwards will have a ReLU. And then we'll have one more fully connected layer. 10 big. And this will be softmax. So that's how we get from our last convolution output to our final result. We always throw it into at least one fully connected layer and sometimes two. Okay. I'm going to look at an alternative for how we could do that in a moment, but let's just look at what's going on. So we've got our model, which has, when we flatten, that doesn't, right, flattening doesn't have anything to learn, so there are no parameters there. When we go to our fully connected layer, why 36928? Let's just think about that. We have 3 by 3 by 64 coming in and 64 going out. Let's see if that makes sense. 64 is 2 to the 6th, times 64 is 2 to the 6th, so 2 to the 12th. So that's about 4,000 times 9, which is 36,000. So it just happens to be the same values as we have up there. And then from 64 to 10 is 650. Why not 640? Bias. Yeah, the biases of 10. I probably forgot about the biases of 64 here, but since I was rounding, I didn't notice. So we got 93,000 parameters to train. Does it make sense? All right, let's look at the training. We load the data, which we had done at some point before. We convert the values from 0 to 255 to a floating point number between 0 and 1. We convert these to be categorical, which means we go to 1 hop. And then we do some training, which is pretty quick, but we just do 5 epochs with a batch size of 64. I believe this is using the GPU. And so we end up with an accuracy of 90, almost 99%. Okay? I said our accuracy was 80 something, 90 something, so we were actually not bad in our accuracy. You might say 97.8 to 99.3, in this case 98.9. Is that a large increase? Well, if you look at it absolutely, from 97.8 to 98.9, that's only like a 1% bump. But if you look at it in terms of how far away you were from 100%, it's really good. Right here, we were 2.2% away, and now we're only 1.1% away. So we're like 50% better, right? We've gone 50% different, the distance to 100%. And this is like all defaults, right? We're not changing the learning rate. We're just doing a pretty simple con. Right? A couple cons, we're even losing some data as we go from one because our pooling is going from odd to even. Not too complicated. Questions? So very common, this is what you're going to see on a convolutional neural network, is you'll have this convolution part of it, and at the very end we tack on what's called like a head, which is the fully connected layer, or layers.
So it seems like in this we've hard-coded the size of the input images. Do they have to all be the same size? Is that specific to this or in general?
They do have to be the same size with this case, with this particular. I'm trying to think whether Keras allows you to specify that sort of we don't know the size. Because if you think about it, really, if our input were not 28 by 28, but we're just sort of x by y, then this would be x minus 2, y minus 2. This would be half that, and so on. So the difference would be kind of how big this is coming out here. But really, it should be able to work with any size input. I don't really remember whether Keras allows you to specify an unspecified input dimension. Okay. Here's what I want to show you. I want to not use any fully connected layers, at least not explicitly. I want to show you that convolutions can take the place of fully connected layers. So this is way over here. It's on. Let's take this 3 by 3 by 64, and I'm going to move this over here. So we did the same previous stuff. We got to our 3 by 3 by 64, and let's look at then what happens after that. We did have a fully connected layer that went to something of size 64 after the flattening. I am going to propose that we use a convolution 3 by 3 so 64 3 by 3 convolutions. Let's look at a single convolution. So a single convolution, so this is our input. The first convolution, what are its dimensions going to be? Well, I'll help you out. It's a 3 by 3 con. So the first two dimensions are 3 by 3. How deep does it need to be? 64. Where's that 64 coming from? From the input. That's right. This step matches this step. That's the first one. How many of these do we have? 64. That's this one. So this 64 is this 64, and that 64 is that 64. What is our output going to look like, though? Someone else want to take over the baton? Go ahead.
It's also 3 by 3 by 64, because each layer is split into one dimension.
Now, hold on a second. Its output is 3 by 3 by 64. Why?
Because there's 64 kernels.
Okay, so I will grant you the depth is 64. I'm with you there. The 64 here is this an underlined 64 or a circle 64? Is that this 64 or this 64? It's this one. So it's that 64, right? Because the number of kernels determines your new depth. That's the convolution. Okay, and what about the height and the width?
Well, the input's 3 by 3.
I agree. The input's 3 by 3.
And the padding.
What padding have we been using for this?
1. Or this is 0. So
We've been using 0 padding. So if we do 0 padding, you get a 1 by 1. I don't know what happened to that. Oh, there. 1 by 1. Right, now I want you to look at a couple things. How many elements are there in this 1 by 1 by 64? 64. How many are there in this 64? 64. How many weights are there here? There's 3 by 3 by 64 times 64. Here, there are how many weights? 3 by 3 by 64 times 64. Ignore the biases for a moment. It's the same thing. This convolution is really the exact same thing as a fully connected layer. Because it's basically saying, for every one of these 3 by 3 by 64 inputs, I have an associated weight. I multiply the input by the weight, I add them all up, and I get a single number. That's this number. And then I do it for the next kernel, and the next kernel, and the next kernel, and the next kernel. That's the same thing as saying I've got a fully connected layer, right? And we have a bunch of weights going into here. So I take weight times input, weight times input, weight times input, weight times input, at a bias, that's the output. And then I do the same thing for this one, the same thing for this one, the same thing for this one. So how we're calculating this first value here is identical to how we're calculating this first value here. But I'm still in the convolutional land. Let's say I want to still live in convolutional land. So I'm going to take this 1 by 1 by 64 and turn it into a, in this case I went from 64 to what? To 10. So let's go to 10. So I'm going to do a convolution. What kind of a convolution? 1 by 1. How many? 10 1 by 1 convolutions. So I have these little 1 by 1 convolutions. How deep are they? 64. And I have 10 of them. So what do I get as output?
So 1 by 1 by 10.
1 by 1 by 10. If we use the softmax, well, the same values here as we do there, we still will probably need to flatten this because this is a three-dimensional thingamabob as opposed to a one or two-dimensional thingamabob here. Let's in fact try it. Let's see if we can do this in 4 minutes. So let's, instead of adding a flatten here, so let's do this. So let's see, we want to add a conv2d. Let's go ahead and steal one of those. Here's a conv2d. So we will add, how many of these do we have? 60, was it 64? Yeah, 64 3 by 3s. And then after that, we had a 1 by 1. And how many of them? 10. And what activation do we want? With these 10? Softmax. And now let's do a flat. The very end. Okay? So let's try this. Let's run it all. Come on, how hard can this be? All right, so there we go. Looks reasonable. It's running, so that means at least the shapes of things seem fine. All right, so what I want you to get out of this basically is, if you have fully connected layers, you can replace them with convolutions. And you'll see 1 by 1 convolutions, and you'll think, what? And this is the reason for it. So we can just sort of stay in convolution land longer. And let's see how this does. I would expect it to be identical, I guess. So, close. Any questions? Your homework is basically you're given an architecture of convolutional networks. I haven't posted this yet. I'll do this afternoon. So you get a hard copy. And you're basically coming up with, for this architecture, what are the actual sizes and so on. I've given you enough information to do this. Don't forget the biases. And you're gonna have to figure out things like, so every convolution layer has the same padding and stride, but I haven't told you what it is. So you're gonna need to figure it out. And then there'll be some calculator work to figure out these sizes. Have a good weekend.